So the next technique that we'll see is trigonometric integration. And what this refers to is basically substitution with a trigonometric function. So it's a special subcase of substitution. And let's see how this works based on an example. So let's say we have to calculate the integral of the tangent function tan x dx. So at first, we don't really have a hard and fast rule to make sense of that. So let's write the tangent as sine over cosine. And then if we do that, what we see is, well, we have a cosine. And if we substitute the cosine, we're going to have to take the derivative of it. That's going to give us a sine, and we do have a sine in our integrand. So let's try that. Let's call this cosine of x, let's call that t. T is cosine x. And then dt is the derivative minus sine of x dx. So we have that sine x dx in our denominator, in our numerator, and those two combine to give us minus dt. So that then reduces our integral to minus dt over t, and that's something that we can solve. This gives us minus logarithm of absolute value of t plus the constant. And now back substituting for t gives us minus the logarithm of cosine x plus the constant. And this is good enough as an answer, but we can make it a bit nicer. This minus here, we can bring that into the logarithm, because we know that a times the logarithm of b is the logarithm of b to the power a. And so in particular, minus 1 times the logarithm of b, that's the logarithm of b to the power minus 1. So that's ln of 1 over b. Okay, so let's use that rule. This is logarithm of 1 over absolute value of cosine x plus c. We can also take out the absolute value and write this as logarithm of absolute value of 1 over cosine x. And so this then becomes logarithm of absolute value of the secant function plus c. So if you remember any of these forms, or if you know how to derive any of these forms, then you can pretty much derive the other just by some algebraic manipulations. But we're going to use this one a couple of times in the next few slides. Oops. So all of these forms are equivalent, and depending on your problem, one might be easier than the other. So there are a couple more trigonometric integrals that you can tackle like this. So you can also look at the integral of cotangent of x dx, and that will give you the ln of absolute value of sine of x plus a constant. So I'll let you do that yourself. And for that you'll have to make the substitution t is cosine of x. T is sine of x, sorry. And then a few more. So this was 1, 2. So for this example I want to calculate a bit. This is going to be an important integral to keep in mind because it's going to come back a couple of times. And it's the integral of secant of x dx, or in other words, the integral of dx divided by cosine of x. So here the substitution is not so straightforward, but what we can do is we can rewrite the integral as secant of x tan of x, and then secant of x plus tan x dx. So So we haven't changed the integrand, we just multiply by a fraction that reduces to 1. But now what this lets us do is it lets us take the denominator here and call that u. That's our substitution variable. U is secant of x plus tan x. And now if you take the derivative d of u, you can calculate it, but you have the rules for the derivative of secant and tan. This will become precisely what you have in the denominator, secant of x times secant of x plus tan of x dx. So this whole thing, with parentheses here, that becomes d of u. And therefore our integral now becomes d of u divided by u, which gives us logarithm of absolute value of u plus a constant. So logarithm of secant of x plus tan x plus a constant. So you see, sometimes these substitutions are really not straightforward, and you have to probably make quite a lot of false starts before you find something that works. That's a bit the trickiness of integration, and that's why you have to practice a lot. The other formula, so the integral of cosecant of x dx, so in other words, dx divided by sine of x. It's a completely similar calculation, and that'll give you the logarithm of the absolute value of cosecant of x minus the cotangent of x plus a constant. So again, please check this if you want to have some hands-on experience doing this kind of trigonometric substitution. So for this example, for the first example, what we're going to look at is the integral of sine to the power 3x times cosine to the power 8 of x dx. And before we try to find a substitution, we have that odd power of sine here. So let's try to write everything as a function of cosine. Let's pull that sine apart to say sine squared x sine x cosine to the power 8x dx. Sine squared I can write as 1 minus cosine squared. So I have a bunch of cosines and then a lonely sine here. So that's actually a good place to be in, because now what I can do is I can substitute t is cosine x, dt is minus sine x dx, and that lonely sine here is going to help me because I can combine it with the dx to give me minus dt. And then I'm also going to get rid of the cosine squared, that's t squared, and the cosine to the power 8, that's t to the power 8. So my integral then becomes minus 1 minus t squared, t to the power 8 dt. So I get t to the power 10 minus t to the power 8 dt, and that gives me t to the power 11 divided by 11 minus t to the power 9 divided by 9 plus a constant. And then back substituting cosine to the power 11 x divided by 11 minus cosine to the power 9 x divided by 9 plus a constant. For the second example, let's do something similar. Let's look at the integral of cosine to the power 5x dx. So again, we have an odd power. So let's write it as cosine to the power 4 times cosine x dx. And I hope you see the pattern here. I'm going to keep that cosine x dx aside, because if I make my substitution, probably these two terms are going to give me the differential. And so what I can do to get to that point is I can look at the cosine to the power 4. So that's cosine squared squared. And I can turn it into a bunch of signs by writing this as 1 minus sine squared x squared. So I get 1 minus sine squared of x squared cosine x dx. And now my integral is nicely set up for substitution. I can call t sine of x, and then this term becomes t squared. dt then becomes cosine x dx, and as I already predicted, these two terms give me just my dt. And so now writing it all in function of t, I get 1 minus t squared squared dt. It's a polynomial, so I expand it. 1 minus 2t squared plus t to the power 4 dt. T minus 2 divided by 3 t to the power 3 plus t to the power 5 divided by 5 plus a constant. Don't forget the constant. And now back substituting sine of x, so we get sine x minus 2/3 sine to the power 3x plus 1/5 sine to the power 5x plus a constant. So for the next example, we'll look at the integral of an even power of cosine, so cosine squared dx. And here, if you try to set aside a power or a cosine or a sine to do a substitution like we did, it's not going to work. But what you can do instead is you can use one of our trigonometric formulas. So cosine squared, that's 1 plus cosine 2x divided by 2. So the integral becomes 1 plus cosine 2x divided by 2 dx. So if you don't remember this formula, have a look back at trigonometry. So all of these formulas will come in handy here. And so with that decomposition, now what we have is 1/2 integral of dx plus 1/2 integral of cosine 2x dx. And so now integral of dx, that gives you x divided by 2. And then integral of cosine 2x, that's again a small substitution of the kind that we've already seen. So if you call this t, then dt will become 2 times d of x. And your integral here will give you integral of cosine t dt over 2, which is 1/2 sine t plus a constant, or 1/2 sine 2x plus a constant. So putting everything together, then we get sine of 2x here divided by 4 plus my integration constant. You can also do the same thing for sine squared, and there you should get that sine squared is equal to x over 2 minus sine 2x divided by 4 plus a constant. The calculation is exactly the same as the one for cosine, so I'll leave it to you to try this out. And now let's look at a higher power. So integral of sine to the power 4x dx. Again, you probably won't be able to set aside one sine to do a substitution. But what you can do is you can follow along with the rule that we used before. So you can write this as sine squared x squared dx. And then you can use the other rule that we know, which says that sine squared of x is 1 minus cosine 2x over 2. So now if you substitute that in here, so we maybe give it a color. So we use this for what I'm about to write. 1 minus cosine 2x divided by 2 squared dx. And by the way, we used this expression for cosine, we used that here, just to make it nice and clear. And so now that we have that, we can calculate. We can expand the square. We get 1/4 and then 1 minus cosine 2x squared. So 1 minus 2 cosine 2x plus cosine squared 2x dx. And now I'm running a little bit out of space here, so let me continue on the right hand side. So now I can use the rules that I already know. So integral of 1, that's x, so I get an x over 4. X over 4. Integral of cosine 2x, I've just derived that, that's 1/2 sine 2x. So I get minus sine 2x over 4. So that's this term right here. And then last, cosine squared of 2x. Well, I know how to derive cosine of x. I've done that here. Integrating cosine squared of 2x, that's another substitution that you have to do. But what we can do is we can reuse what we already know, x over 2. X over 2 plus sine 2x over 4. So let's maybe do that quickly on the side here. So for integral cosine squared 2x dx, if we call this t, then we get that this is cosine squared t dt over 2, and therefore reusing our formula that we derived earlier, we get x over 4, t over 4 sine 2t over 8 plus a constant, and then replacing again t by 2x, we get x over 2 sine 4x over 8 plus a constant. So let's add these terms to what we already have. So the result of my side calculation here appears at the bottom of the slide, and I'm going to transfer it here now. So I get plus 1/4 x over 2 plus sine 4x divided by 8, and then plus a constant. And I'm going to have just enough space to write the final answer. So the x over 4 and the x over 8 here combine to give me 3x over 8 minus sine 2x over 4 plus sine 4x divided by 32 plus a constant. So this is my final answer for the integral. And then two more examples involving the secant and the tangent function. So let's do the same thing for the integral of tan squared of x. We haven't worked with tan so far. So here, there's also something that we can do to make this more nice. So we know that tan squared can be written as secant squared x minus 1. And so therefore, our tan function integral becomes secant squared minus 1 dx. And that integrates straightforward to tan of x minus x plus a constant. So why is that? Well, integral of secant squared x dx, that's one that we know from our table. It's tan x plus a constant because d dx of tan x is secant squared. So this one is a bit special. Now let's look at the integral of secant squared x dx, or sorry, secant to the power 4. Secant squared we know. So we get, from this rule, we get that secant squared x is 1 plus the tangent squared of x. So here we can write it as 1 plus tangent squared x times secant squared x dx. So let's pause for a second. This is also a manipulation where you might say at first sight, well, hey, why do you write it like that? Why don't you write it as 1 plus tan squared squared? Why not go all the way and get rid of the secant altogether? That's a reasonable intuition. You can try that and probably you will not get very far. So again, with many of these substitutions, sometimes you have a few false starts before you hit on the answer. There's no golden ticket to say this is what you have to do to integrate. It's always a bit intuition, a bit trial and error, and then finally getting to an answer. So here the reason why we write it as this with tans and secants is because we know a little bit that there's a relation between secant and tan. So by writing it like this, we hope that we can make a judicious substitution and then have everything work out just right. And this turns out to be indeed the case, because now what you can do is you can substitute tan of x for u. So write u equal to tan of x. And then you have du is the derivative of that, so secant squared x dx. And you have precisely that secant squared x dx here. So this will combine to du. And therefore my integral becomes 1 plus u squared du. We'll get u plus u to the third divided by 3 plus a constant. And substituting tan again, we get tan of x plus 1/3 tan to the power 3 of x plus a constant.